Hello and welcome to Saturday's edition of Cracking the Cryptic, where today we've got a puzzle by Brandon Bot for you. And this intriguingly, well, it's called WYSI, which meant nothing to me, but I looked it up and apparently it's internet slang for when you see it. And on Logic Masters Germany, Brandon Bot says that this puzzle is apparently based on the most frustrating video game that he's ever played. And apparently the colour and the cage totals, which you see seem to be 7s and 27s, is somehow thematically related to this. Now, unfortunately, I have absolutely no clue what video game this could be. I am intrigued to know. I'm going to have to rely on you guys to explain this one, but our testers have tried this puzzle and apparently it is a work of some genius, so it should be an absolutely brilliant puzzle to have a go at. Now, before we do that, do have a look. If you've not had a look at it already, there is this incredible Sudoku Extravaganza on Patreon at the moment, which is by Jovial, and Jovial has created no less than 20 Sudokus of sort of approachable difficulty, covering every single variant that you could ever think to see on the channel. There's Arrow Sudoku, Killer Sudoku, Clone Sudoku, XP Sudoku, I've already said Arrow Sudoku, Thermo Sudoku, Between Line Sudoku. There's all sorts of things. Kropki pairs Sudoku, quadruple Sudoku. There's stacks and stacks of beautiful, beautiful puzzles. And yeah, I just recommend that you have a go. It really is a treat. And we're very, very thankful to Jovial for creating it for us to share with you. Now, let's get on to Brandon Bot's puzzle. What are the rules? And in fact, I can get rid of the colours. Apparently, I've been told to get rid of the colours for solving it. So I'm going to try and do that now. Now, the rules. Normal Sudoku rules apply. In cages, digits must sum to the small clue in the top left corner of the cage. Digits cannot repeat within a cage. So that's normal killer Sudoku rules. So those 4 squares there have to sum to 27 without repeating a digit. On the marked blue diagonal, digits cannot repeat. So we just have one main diagonal today where we've got to make sure those highlighted cells there have to contain the digits 1 to 9 once each. And that seems to be it. So do have a go. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. And I have a feeling I might know how to start this one, because I imagine we have to use the one fact I know about 27 cages, which is that a 4-cell 27 cage must contain a 9. Now, how do I know that? Well, I think it's from doing a lot of Kukuru over the years. Kukuru in 8 plus 7 plus 6 plus 5, if we just do that, 8 plus 7 plus 6 plus 5 only equals 26. So, we must have a 9 in that box somewhere. We must have a 9 in that cage, in that cage, in that cage. Oh, goodness me, I've just seen there's a 1, 2, 4 triple in a 7 cage. Sorry, I missed that. That's an easy win. Although I'm not seeing what that 7 cage does. But let's come back to the 9 cages. Or not the 9 cages, but the cages that have to contain a 9. And see if we can spot something. And the answer to that is maybe not, actually. I can see if either of those are 9. You'd lock a 9 in here in box 9. So if that's a 9, there'd be a 9 in there. There'd be a 9 here, and there'd be a 9 in there. Ooh, no, sorry, I'm not seeing anything straightforward there. So apparently that's not how... Oh, is it the secret? No, I don't think it is, but just if you're new to the channel and you don't know the secret, there is a very important secret that will help you with Killer Sudoku, relating to the fact that any complete box of a Sudoku, any complete row, or any complete column will obviously contain the digits 1 to 9 once each. If you add up the digits 1 to 9, you get 45. 45 is the secret. Now, that means if we think about this box, look, as this cage adds to 27, those 4 squares must add to 45 minus 27, which is 18, to ensure that that box overall adds to 45, and that unfortunately doesn't mean anything to me. no, it really means nothing. You don't have to have a 1 in those 4 cells, because you can easily make totals like 18 without a 1 in 4 cells. So the expression I think we're looking for at this point is bobbins, and we probably have to think about the 7 cages, of which there are 4 dominoes of 7 cages. So, right, okay, I can see something here. Okay, yeah, maybe there is something. We can use colours to show you the somethings I've found. So let's just establish why 7 in 2 cells is interesting. And normally I wouldn't think it was very interesting, but basically it can be made up in 3 different ways. So this could be a 3-4 pair, a 2-5 pair, or a 1-6 pair. Now, whatever this is, whatever this domino is, obviously this domino cannot be the same. So if this was 1-6, this domino, you can't put a 1 or a 6 in this cell, so this has to be a different composition to this one. So we can colour it differently. Let's use green for this one. Now, what I just noticed is that this one now cannot be green and it cannot be purple. Why can't it be purple? We can see it can't be green because whatever, let's make this one, I don't know, 2-5. If that's 2-5, you can't put 2 or 5 in here. So this definitely is not green. Why is it not purple? Well, it's not purple because of Sudoku, of all things. If you put purples in both those squares, 2 of those 3 squares must be purple. And that breaks the 27 cage. Because if 2 of its cells add to 7, the other 2 will have to sum up to 20, which is impossible. So that's actually quite beautiful. And it means that's not purple, and we know it's not green, so we can make it blue. Now, what's this one? This one's clearly not blue. Ah, bother. This one can be green, look. Ah, this is annoying. I was thinking we were going to be able to... I was thinking we were going to be able to show that this was purple. But I don't think we can, because if this was 2-5, for example, there's nothing preventing that being 2-5. So long as we keep this from being 5, this could still be a green domino. And that's very annoying. Well, at least maybe not very annoying, but it certainly doesn't mean that we can just colour this one in. So what's this telling us then? Just give me a second to stare at this for us, if you don't mind. I feel like there must be something here, because this... It definitely feels deliberate that these 2 can't be the same. Ah, I see. I think I've seen it. Right. That is absolutely gorgeous. This is a beautiful idea, actually. It really is. Let us consider where the digits in blue go in column 3. That is a very interesting question, because obviously whatever's in here can't go there. That would repeat in the box. And they can't go in green because we know that green is a different composition to blue by definition. So, how are we going to split up these 2 digits between these 2 cells and these 3 cells? And I think the critical point is that you can't put both of these cells in one of these cages, because it won't work. If you put both of these cells in here, the other 2 cells have to add to 20. If you do it there, these 2 cells have to add to 20. That doesn't work. So you have to allocate one of these cells to one of the 27 cages and the other cell to the other 27 cage, while still enabling the 27 cages to work. So this must be 3-4. And why do we know it must be 3-4? Well, it's because if we try anything else, let's try 2-5. Let's allocate the 5 down here. Let's just say this is a 5, and therefore this is a 2. This cage works beautifully. It has a 5 in it, the other 3 cells have to add to 22. That's absolutely possible. This cage is absolutely broken because you can't make 3 cells add up to 25. 9 plus 8 plus 7 only equals 24. And of course with 1 and 6 you're just going to exacerbate the problem in one of the cages. So you can't do it. You cannot make it work. That is so clever. So this is 3, 4. And one of these cages has a 3 in it. And we'll have to accompany... That'll have to have a 7, 8, 9 with it. And the 4 will have to have a 6, 8, 9 with it. But I don't think we know which way up this goes. Do we? I know that both of these cages now have an 8 in them, because one of them is a 4 with 6, 8, 9. One of them is a 3 with 7, 8, 9. I'm not sure. Sorry about this. I'm not quite understanding how to do this. Let me think about this one again. Have we learnt more about this from restricting these? Oh no, sorry. I thought I was onto something, but I'm not. If this is purple, what's that telling us? If this is purple, that's saying that one of the digits in purple, this one, would have to go in the 27 cage. That would be beautiful. That would be absolutely beautiful. Because then we would know that this was the cage that had a 6 in it. Now if this is green, let me just think about that for a second. Can we prove that this is not green? That's the question. If this is green, that domino is now purple. And is there anything wrong with that? That's the next question I'm asking myself. I don't know. This is quite tricky, isn't it? Is there anything wrong with that being purple? Then this would be purple. One of these is in blue, one of these is in blue, but that's fine. That's what we're expecting. I'm not quite understanding this for sure. Sorry, I just made that the wrong colour. What about... Oh, good grief. Right, that's really strange. I've just spotted what's going on with my Neapolitan ice cream. Wow, okay. What's the right way to explain this? It's not straightforward. This is broken. Okay, why is this broken? Well, it's because this digit and this digit have to be the same in the 7 cage. You can think of it, let's just do an example. If that's 2, 5, this will have to continue and be 2, 5. And the critical thing about this, I think, is that this square is now green. And that's impossible. Because if this square is green, now blue in box 1 has to be both. The only places for blue are in those 2 squares, which breaks it. So this is not green. That's what we can say. Wow. Sorry that took me a while to see. There may be an easier way of spotting that, but I couldn't see it. But that is good logic, isn't it? So now we can say that as this is not green, it must be purple. And this is good. This is what I was hoping for, because now, why I'm excited about this, now I'm interested in this digit. Because this digit, by the power of Sudoku, has to go in the 27 cage. And if it has to go in the 27 cage, what can it be and the 27 cage work? Because remember, one of these 27 cages is a blue digit, the 3, accompanied with 7, 8, 9. So that cannot be this one now, because you can't put a 7 in here. That will have to be a 0, and that will break it. So now we actually know that this digit has to be 6, because we know the cage that gets allocated the 4 has to be 4, 6, 8, 9. So this one must be allocated the 4, and it must be 4, 6, 8, 9. And we actually know all sorts of things now, because we now know there's a 3 in one of those squares. We know there's a 7 in this cage. We know this is a 1, 6 pair. We know this is a 2, 5 pair. And we have... do we have more? Yes, we do, because where does 4 go in this box now? It has to go here. Yeah, that was probably the simpler way of seeing what I saw before, wasn't it? So the moment you realise that you have to allocate this 1 to this and 1 to this, you know that this is blue, and therefore you know that's not green. It's the same logic, just in a different order, and it might have made it easier for me to see it. Now, there has to be a 3 in one of those squares by Sudoku now, because we can't put 3 in this 27 cage. There has to be a 1 in one of these cells. This is not a 4 or a 6 because of the 6 in the 1, 6 pair. So this is 8, 9. Whoa, I keep pressing the right mouse button by mistake. And what else can we do? Well, we can use the 1 on the 7 cage now. That gives us another digit. In fact, it gives us another 2 digits by the power of Sudoku. You can never put a 1 in a 27 cage of 4 cells, so there's a 1 over here. There's no 1 in there. There's just 2s and 4s now, so this is not 4. 2 I can place in box 7 by the power of magic. No, not really, by the power of Sudoku, because we can't put 2 in the 4-cell 27 cage because the other 3 digits would have to be too high. You can't make 3 digits add 25. So the 2 in box 9 is not there by Sudoku, and it's not in the 27 cage by maths, so it's in one of those 3 cells, which means in this box it's forced into that cell, which means now by Sudoku this is the only place a 2 can go, in box 1, which makes this a 5. And now we ask where a 5 goes in column 2. It has to go in those squares, which makes this square a 7 by Sudoku. Ah, this is important. This 7 is important because now we have to ask where 7 goes in this box, and it has to go there. So this is now a 3, 7 pair, which means this is an 8, 9 pair to make that cage add up. And now we know those squares have to be precisely 5s, 8s and 9s. And we have a 2 on this diagonal, which means that's not a 2. And now we know... do we know more? Can we get this digit? That feels like it would be a useful digit. It's got to be... oh, it's got to be 8 or 9. I see. It's got to be whatever that is, because this digit still has to appear in column 3. So those 2 squares are the same. I'm going to colour those in. Okay, I'm going to get rid of the 3 pencil mark there and take a stare at the grid and see what we can see. Now, what on earth do we do next? Do we know... do we know anything about anything? That's the question I'm asking. 1 is very nearly restricted on this diagonal, because this 1 is ruling it out of those 3 cells. It can't go in a 4-cell 27 cage. Unfortunately, I think it can go here, and it can go there. So 1 on this diagonal is in one of 2 places, which means inter alia it cannot go there, because if there was a 1 here it would rule 1 out of both positions on the diagonal, which is a very long-winded way of saying that no, I don't know what the next step in the puzzle is. I'm going to have to think a bit harder. There's definitely a 4 in one of these squares. There's an 8, 9 pair. Oh, good grief. Right, there's an 8, 9 pair here, so there's no 9 here. Is that going to matter? That means there's a 9 in one of those cells. 27 cage? I've not thought about that yet. Do we know anything about that? We know... yes. There is something. Good grief. Right. I'm not quite sure what this means, but I have spotted something about the 27 cage. Now, it's a 6-cell cage. Let's ask the question. Let's imagine we saw a 9-cell cage in this puzzle. What would it add up to? It would add up to 45. Because we can't repeat digits in cages, a 9-cell cage would contain all 9 digits. That adds to 45. We know that because of the secret. Now, this cage is therefore missing 3 cells that sum to 18. But one of those digits that it's missing is a 1, because you can't put 1 in those 2 squares by Sudoku, and you can't put 1 in those 4 squares again by Sudoku. So this box or cage is missing a 1, and then 2 digits that sum to 17, which must be 8 and 9. So there's no 8, there's no 9. In fact, we know the composition of this cage. I'm going to do something I don't often do. I'm going to ludicrously over pencil mark this. There's a 2-4 pair there, just to see if I can spot anything interesting. Does this matter? Oh, it does. I've got red. This puzzle is beautiful. It really is. This is very impressive. Now look at 9 in this 27 cage. I don't know about 9, or I don't know much about 9, but I do know it's not in that domino, because of we know the 9 in row 4 is in one of those 3 squares, so it's definitely not there. Now that means, just look at box 6 and ask where the 9 goes. Therefore, it's vertical. It's in one of those 3 squares. And therefore, the 9 in the 27 cage down here is not in those 2 squares. Therefore, the 9 is horizontal, which means this square is an 8, which means that square is an 8. Which means what exactly? Does that mean... Do we know something about this 27 cage now? Or not? I feel like I must know something about this. What is it? I'm not sure. Sorry if there's something that I should be appreciating there, but I'm just not seeing what it is. 7 has to be in one of those 6 cells. 8 I can see is not in those squares, but I don't think there's anything wrong with there being an 8 in the 27 cage. Okay, no, I think I'm stuck. I suppose now I know what those 3 digits are. What are those digits? They are 2, 7 and 9. Does that mean anything to anybody? That's not 9. No, I'm not sure. The owls are hooting at me now. They presumably know something about the puzzle I don't. Okay. What do we know? Is it something... How on earth do you get a grip on this? I don't know. Normally with diagonal puzzles I quite like to focus on the digits that are not on the diagonal. But here I know very little. I know that 3 and 7 are not on the diagonal. 3, 4 and 7 are not on the diagonal in box 1. So 3, 4 and 7 have to appear in 3 of those 6 cells. Do we know more than that? Can I do anything with this? 3, 5, 6 and 7 here. Oh, I might be able to actually. Let me just think about that. Because I've got a 3-5 here. So this cannot be a 3-5 pair. And it can't be a 6-7 pair. Good Lord, right. Right, this is interesting, I think. Because, why do I say this cannot be a 6-7 pair? Well, if it's a 6-7 pair, the 27 gauge is broken. Because, let's try and make it work if we can't use 6 and 7. 9 plus 8 plus 5 plus 4 is, I think, only going to equal 26. So I need a 6 or a 7 in this cage. But I also know, so I need a 6 or a 7 in this cage. And I can't have both. Because if I have both, this becomes a 3-5 pair and breaks that. So there must be exactly one of 3 and 5 in this domino, and exactly one of 6 and 7 in this domino. Does that mean I have to put 8 in here? Please let that mean that. If there is no 8 in here, and there's only one of 6 and 7, then the highest I could make this add up to would be 9 plus 7 plus 5 plus 4, which is nowhere near enough. Wow. So there is an 8 in this 27 cage, and it has to go there by Sudoku. That's really clever. Now, have I now got somewhere there's an 8 in one of those two squares because of this 8-9 pair here? So, bear with me, I'm trying to get somewhere here. So I know there's a virtual 3-5 pair here. So this square has to be 6, 7 or 9. Do I know which of those it is? I don't think I do. I really don't think I do. 8 in the central box has to be in one of 4 positions. Oh, 8 in box 6, look, it's locked into the same squares as the 1. That's probably important because that means 8's in one of... Ah, no, I can place 8 in box 5, look, by Sudoku. It can't go on the diagonal and it can't go there by Sudoku, so it's actually locked into that square, which places it down here. Which, how many 8s have I got now? I've got 5 8s placed. I can probably get more 8s, but I'm not seeing immediately how to do that. So now I know those 3 squares, of course, because they must be... Oh no, I don't. Ah! No, I don't. I was thinking I knew these because they're so heavily pencil marked, but in fact, because I don't know those, I don't know these. Oh no, I really don't. Ah, look at this one. You can't put an 8 in this 27 cage now. So if you can't put an 8 in it, how are you going to make it work? It must be 9, 7, 6, 5. And there's a 5 here. That becomes a 5. This puzzle is sensational. 6, 7 and 9 go in. That gives me a 2. That means I get rid of 2's in those cells. This square's got to be a 3 or a 4 now. 6, 7 and 9. There's all sorts of things going on now, but I'm probably not spotting the obvious things. Ah! How long have I had? Nearly half an hour. I'm not too embarrassed about that. I definitely don't think this is an easy puzzle. Can I get more joy about what's happening anywhere here? 2. I suppose 2 and 4 have to occupy those 2 of those 4 cells. I might as well notate that. Now we know this cage definitely has an 8 and a 9 in it, so that deals with 17 of the 27. So it's either got 3 7 or 4 6 as its other digits. Do we know which? Yeah, we do. Look at that square. Wow. If this was 4 6 9, that square has no value. So this is 3 7 9. Jeepers creepers. That means that that's a 5 6 pair, which means this becomes a 9, this becomes a 7. That removes 7 from here, removes 9s from here. And suddenly we might be, that can't be 9, because the 9's definitely in those squares. Are we cooking with gas? We've got 1 2 4 along the bottom row. That's not a 2 because of the 2 on the diagonal. That sees this 4 6 pair, which resolves it. And now we ask where 9 goes in box 8. I think it only goes in that cell, which means that square becomes a 6. Have we got any more? Ah, now that square, look, has got to be a 3 or a 5 to complete the row. We're very close to having some sort of triple or quadruple down there. Okay. 1 has to be in one of those 2 squares. And what's the other digit that we don't know about here? 5, I suppose. 5 has to be in one of these squares. 5 and 6. Ah, here we go. Here we go. 6 on the diagonal. Where's it going? It's not in those 3 squares. It's not in these 3 squares because of this 6. So it's got to be exactly there. That's the only place it can go. That gives us a 1. Now what? Yes, beautiful. Now 1 isn't on the diagonal in these 6 cells. So 1 must be in one of these 3. It must be there. We get a 1 on that, gives us a 1 and an 8. 1s are in one of those 2 squares. This is now a 2 4 pair. Don't know what this means yet, but it does feel like it's a little bit more progress than we were making. Come on. Where is the next deduction coming from? We've got loads of high digits in column 6. We need 1s, 2s, 3s and 4s, so that's a 1 or a 3. This square is a 2, 3 or a 4. That square is a 2, 3 or a 4. Bother, and that's a 1, 2, 3 or 4. So feel like we must be about to crack this. Oh, I've got a 5 6 here, so that's a 3, that's a 5, that's a 3. Ah, that gives me a 4 here on the, that's on the diagonal. That gives me a 4 and a 2 there. This square now is not a 4, so this is 2 or 3. Oh, it can't be 2. Sorry, 2's on the diagonal. So combining the 2 and the 4 gives us this digit. Therefore, there's no 3 here. We're down to 5s, 7s and 9s on this diagonal, I think. So this square, oh, I don't believe it. It can be any of them. It can be 5, 7 or 9. This 3 is giving us a 1 beneath it. That means we can get rid of 1 from there and 3 from both of these squares. And we have found a little 2 4 pair in box 2. And we know that the rest of the digits in this box are 1, 3, 6 and 7. And we can probably do some magic with that, but I'm not immediately seeing how to. That can't be 1, that can't be 6. So I'm thinking about this column now, because effectively, look, we've got 6 digits roughly placed. We've got 5s, 6s and 7s to place. This square, oh, this is a 5 6 pair, look. So this is 5 6 or 7. Oh, this must be resolved. Ah, one thing we could do is eliminate 5 and 6 from the rest of this 27 cage, which does look, that gives us 2, 3, 4, 7 quadruple, which places 9, places 7, places 7 here. 7 comes out of those squares. 6 here is now very helpful. 5, 9 and 2 go in. 5 and 6 goes in. Those probably aren't going to be resolved, are they? Because they look like a triple. They're going to need correspondence from horizontal digits to resolve them. Unless, of course, yeah, the 9 here is nice. So that gets me a 5 on the diagonal, 7 down there, a 3 here, a 9 here. 7 can't be in those squares. 2 and 3 can't be in those squares, so that's got to be a 4. This square is specifically a 4, this is a 7. So these are now a 2-3 pair, which we might not be able to resolve, but it's definitely better than we were doing. And these squares are a 5-6 pair, which we can resolve. And the 4 and the 3 go in, and the 9 and the 7 go in. I don't want to speak too soon, but it does feel like we've suddenly really made progress. There's an 8-9 pair in row 2. I've not even thought about this cage yet. Can we do a bit more? Yeah, we can keep tidying up down at the bottom. 4 and 2, 2 and 3. This column looks good, doesn't it now? We need 1s, 2s and 7s. So that's a 1 by Sudoku, and this is a 2-7 pair. Okay, I'm not sure if we can do more than that. We can get rid of 1 from this square, which places 1 in that box. This row now needs 3s, 6s, 8s and 9s. So this square is either 6, 8 or 9, which is a bit disappointing. This, oh no, this square is either 3 or 6 because it sees 8, 9 in the column. So there's a 3-6 pair so that we can remove 6 from this one, and we now got an 8-9 pair here and an 8-9 pair there. I'm not immediately seeing how to resolve them though. So this is 5, 6, 8 or 9. 5, 6, 8, 9. Let's get rid of what we can. We can get rid of 5 and 6. And 5. Not seeing how to do this. Is that? Oh no! Look, I've got to make use of my 8-9 pair there. That's going to give me a 5. Which doesn't seem to... Oh, no, that gives me a 5 and a 6. I was unfairly maligning this 5 for a moment. Now, what have we got in this 27 cage then? I've now got 14 in those digits. So that means those two squares add up to 13. So we can remove 8 from there because that would repeat the 5. And we can remove 6 from here because that would need a 7. So that should be a 9. And hopefully this can be a 4. Which it does look like it can be. And I think that might be... Not to speak too soon, but that does seem to be resolving everything. 3s and 6s, that becomes a 6. This column still needs a 3. That's going to be an 8. That fixes the 8 and the 9. That fixes the 8 and the 9. What a puzzle. Yeah, that is just stunning. Absolutely stunning from Brandon Bott. The start's really clever. It really is. This idea with the 7s and the way that you can't put 2 digits from the same 7 combination in a 27 cage is absolutely gorgeous. And from there was a lot of very, very nice logic that involved quite a lot of thinking. This domino here, I think I was a bit slow to appreciate how powerful it was, but it really was because it allowed us to narrow down the entries for that 27. And then there was a lot of clever stuff on the diagonal as well. It's just overall an extremely brilliant puzzle. Let me know in the comments how you got on with it. I hope that you got through it and I hope you enjoyed it even a fraction as much as I did. And we'll be back later with another edition of Cracking the Cryptic.